BERT, Reading in Both Direction, Part 5, Pre-Training Mechanics, How BERT Learns Without Cheating. In Part 3, we introduced BERT's core innovation, bidirectional encoding, and the two training objectives that make it possible. In Part 4, we opened the hood, the encoder stack, the model sizes, and the input representation, token, segment, and position embeddings. Now we do what Part 4 promised. We're going to slow down and look at the pre-training mechanics. Not the headline version, but the actual training details that make BERT work, and the small choices that prevent it from taking shortcuts. BERT pre-trains with two objectives: masked language modeling, or MLM, predicting missing tokens using both left and right context, and next sentence prediction, or NSP, predicting whether sentence B truly follows sentence A. You've already seen these ideas at a high level. In this part, we'll focus on what's easy to miss, how masking is constructed, why the 80-10-10 strategy exists, what NSP is really training, and why the data choice matters beyond simply being large. Let's start with masked language modeling. A left-to-right language model can be trained with a simple rule: predict the next token. BERT can't do that because BERT is bidirectional. If the model can see both sides of a token and you still ask it to predict the next token, the answer is already visible. So MLM creates a different learning problem. Instead of predicting the next token, BERT has to infer missing tokens from surrounding context. Here is the procedure. Step 1. Select 15% of token positions. For each input sequence, BERT selects 15% of token positions, at random as prediction targets. And it's worth clarifying what that means. BERT isn't masking words the way humans think about words. It's masking word piece tokens. So a word like playing might be tokenized into play and ing. Either of those pieces can be selected. Step 2. Apply the 80-10-10 replacement rule. Once a position is selected, BERT modifies the input token in one of three ways. 80% of the time, it replaces the token with the special mask symbol. 10% of the time, it replaces it with a completely random token from the vocabulary. And the remaining 10% of the time, it leaves the original token unchanged, but still treats that position as a prediction target. Then the model is trained to predict the original token at that position. At first, this can feel like unnecessary complication. Why not simply replace every selected token with mask? The reason is that mask introduces a mismatch between pre-training and fine-tuning. Now, why does the 80-10-10 rule exist? It's all about fixing the mask mismatch. Here is the mismatch BERT is trying to avoid. During pre-training, the model sees mask all the time. During fine-tuning and in real use, mask essentially never appears. So if you trained with mask 100% of the time, the model could become dependent on a very obvious cue. A token is missing here. The 80-10-10 rule prevents that. The random token 10% teaches the model that sometimes the input is wrong, and context has to override what it sees. The unchanged 10% teaches the model that even when a token looks normal, it may still be a prediction target. So the model can't rely on a special marker to do the work. The end result is that BERT learns representations that transfer cleanly into fine-tuning, where nothing is explicitly masked. So what is MLM really training, and what is it not? One more important clarification: MLM is not trying to reconstruct the entire input. BERT is not behaving like a classic denoising autoencoder that corrupts the whole sequence and learns to rebuild everything. Instead, BERT predicts only the selected positions, and that concentrates learning pressure exactly where you want it. Each masked prediction forces the model to integrate multiple layers of understanding. It needs to understand syntax, what can grammatically fit in that position. It needs to understand semantics, what makes sense in meaning given the context. And it needs to track long-range context, how earlier and later tokens constrain what the interpretation can be. Over time, BERT develops internal representations that generalize across tasks. Not because it was trained on those tasks, but because MLM demands broad language competence as a prerequisite. Next up, next sentence prediction, what it trains concretely. MLM teaches token-level understanding, but many downstream problems depend on relationships between spans. For example, does a premise support a hypothesis? Does a question align with a passage? Do two sentences belong together, or are they unrelated? NSP is designed to teach that kind of sentence-to-sentence relationship. The NSP setup is essentially a controlled 50-50 problem. For each pre-training example, sentence A is sampled from the corpus. Then sentence B is constructed in one of two ways. Half the time, B is the actual sentence that follows A in the original document. This is labeled isNext. The other half of the time, B is a random sentence sampled from elsewhere in the corpus. This is labeled notNext. The model receives both sentences as a single combined sequence. Remember from Part 3 how BERT handles sentence pairs? It starts with the CLS token, then all the tokens from sentence A, then a SEP separator, then all the tokens from sentence B, and finally another SEP at the end. The model processes this entire sequence through its encoder layers, and then makes a prediction. Is this an isNext pair or a notNext pair? What vector makes the decision? NSP uses the final hidden representation of CLS as the sequence-level summary. And this has an important effect. NSP encourages CLS to become a representation that is sensitive to discourse coherence, whether sentence A and sentence B actually fit together. So MLM shapes token representations, whilst NSP shapes sentence pair representations. Here's why document-level corpora matter. It's not just more data. NSP only works if next sentence really means next sentence. If you shuffle sentences randomly, that signal disappears. That is why the paper emphasizes using a document-level corpus rather than shuffled sentence collections. It preserves continuity so next has a real meaning. And it supports something else as well. Long contiguous sequences. BERT is trained on spans, not isolated sentences. Keeping documents intact makes it easy to sample long runs of text where reference, topic flow, and discourse structure are real. The kind of structure MLM and NSP can actually exploit. Why books and Wikipedia? The answer is simple. Two complementary types of signal. BERT's pre-training uses two corpora, BooksCorpus, which provides long-form narrative flow, and English Wikipedia, which provides broad factual coverage, with text passages favored over lists and tables. They complement each other. Books help the model learn continuity, tracking entities, resolving pronouns, and following ideas across multiple sentences. Wikipedia adds breadth, names, concepts, and relationships across a huge variety of domains. Put simply, books give BERT practice in following language over time, whilst Wikipedia gives BERT practice in covering what language is about. Together, they produce a model that is both structurally competent and broadly informed. Let's pull it all together. the coherent picture of why these mechanics fit the architecture. Now we can connect this back to parts 3 and 4. The transformer encoder lets BERT integrate context from everywhere. MLM forces deep bidirectional representations without letting the model peek at the answer. The 80-10-10 strategy prevents pre-training artifacts from breaking fine-tuning. NSP encourages a coherent sentence pair representation via CLS. The corpus choice provides continuity and coverage, and document-level structure makes both objectives meaningful. So, bidirectional understanding isn't just a phrase. It's the outcome of a training recipe that has been designed to make that outcome possible. Coming up in Part 6, we would look at fine-tuning properly. Pre-training gives you general-purpose representations. Fine-tuning is how you turn those representations into working systems: classification, entailment, tagging, and question answering, using the same encoder and minimal task-specific changes.